This session of the SCTE Chattahoochee and South Florida Chapter Virtual Vendor Day is titled Introduction to Fiber Optic Technology. The key learning objectives are why to use optical fiber, what the elements of an optical fiber are, strength and coatings of fiber, a phenomenon known as total internal reflection, index of refraction. We're going to discuss the differences between single-mode and multi-mode fibers very briefly. We're going to talk about attenuation, which is the loss of fiber, the intrinsic and extrinsic types of loss. We're going to go over the different fundamental operating windows or wavelengths. We're going to talk about single-mode cutoff fiber wavelength. We're going to talk about the bandwidth or bit rate limiting phenomenon known as dispersion and what the elements of dispersion are. And then we're going to talk about optical fiber cables. Very briefly, key installation and handling parameters. And then finally, we're going to wind up with a discussion about splice closure systems. First of all, it has high bandwidth, high capability of carrying lots of information. It has low attenuation or low loss, which means long distance between regeneration points. It's light in weight, small in size, and it makes it easy for installation crews to handle and to install. It has no metallic conductors for transmission, so it means there's no ground loop problems, no crosstalk, no outside electromagnetic interference, and it doesn't radiate EMI that might influence other systems. It's passive media, so it means no line powering requirements, and it has no circuit protection concerns. It's very difficult to tap, which means it's very secure, and it's universal media. It can transmit voice, data, or video because it transmits binary codes, which are basically ones and zeros, and a pulse combination of code that regenerates the voice data and the video signals. All the three C's, the core, the cladding, and the coating. The core and the cladding are basically silica glass. They are basically made up of two different materials of glass that have different index of refractions. The coating is the first protective layer for the fiber. It's called the primary buffer, and there are actually two coatings, a soft and hard layer. Typical telecommunications style fiber is based upon 250 microns coated, 125 microns at the cladding, and then depending on the type of fiber it is, somewhere between 8 to 100 microns in the core. In multi-mode fiber, the cores are either 62.5 or 50 microns with 125 micron cladding. Single-mode fiber has a much smaller core at 8.3 microns and again 125 micron cladding. Sophisticated process, but some of the key elements of it are outlined in this diagram. Basically, a glass blank, which is made up of two different materials that make up the core and the cladding, are put through a furnace that brings them the tip of the glass blank almost to a molten state. And the fiber is a pair of tweezers are reached up into the furnace to grab what's called the glob and start the fiber to string or draw. It's pulled down through a diameter laser monitoring system, multiple laser monitoring system that checks the key parameters of the diameter, and then it goes through an acrylite coating applicator that then goes into a UV curing oven and continues to be pulled through using the drawing caspins. A key element of this drawing process is basically the fiber proof testing. The fiber proof testing is basically the making sure that the fibers don't have flaws in the cladding that are any greater than a certain size. To 700,000 pounds per square inch. But all fiber does have small inherent cracks in the cladding. When you stress the fiber, either by pulling it or bending it, you concentrate the stress to the largest crack flaw in that section. As long as the load is applied to the crack, the crack will continue to grow to a point of failure, and this is called latent fiber stress fall. The greater the crack size, the lower the fiber's breaking point. Bending does induce a strain, and that's why recommended bend radiuses long term are 1.5 inches for fiber. And when you see bending diameters, like in splice trays, you typically see splice trays at right around 3 inches. Well, most of the fiber today is proof test around 100 kpsi, and that states then that the maximum crack depth will be a 0.86 micron crack depth. And this all goes into the recipe of the lifespan of the fiber in the cable based on its proof test. Plastic, there's a soft and a hard layer. The soft layer is the first layer, and it basically cushions the fiber. The hard layer basically provides the abrasion resistance. The coating is called the primary buffer. It also provides a hermetic seal to protect the silica fiber from humidity and other hostile environments. The coating has a high index of refraction, the higher index of refraction than the core and the cladding. And basically what this allows for is once the light has escaped from the core into the cladding, it allows the light to continue to not stay trapped inside the cladding itself. It allows it to escape. When you're doing the splicing process, you have to strip the coating to remove the protective layer. This has to be resealed with a splice protective sleeve. We talked about the term index of refraction. Index of refraction really is nothing more than the velocity of light through that material compared to the velocity of light through a perfect vacuum. A perfect vacuum, the only perfect vacuum is in space, and the speed of light through a perfect vacuum in space is 186 miles per second. When you compare the speed of light through silica, silica typically is around 127,000 miles per second. And when you compare this ratio, you'll get an index of refraction for silica glass that's somewhere in the neighborhood of 1.45. Specifically 1.471 at a specific wavelength. Cladding actually holding the light inside the core, and this controls the direction in which the light signal is propagated down the fiber. This process is what's called total internal reflection, and it's the key elements of how fiber optics. When you have a core and a cladding of two different index of refractions, as long as the light is coupled into the core at the appropriate angle, the light will reflect inside the core and stay inside the core. If it's not the appropriate angle, it will refract. This is called a critical angle. Total internal reflection is achieved through keeping the light signal inside the critical angle. And the critical angle is a function of the index of refraction between the core and the cladding. So if you look at photons, these are not Pac-Man, these are little photons. Photons travel at different speed through different materials of index of refraction, as we talked about. So the lower the index of refraction, okay, the faster the light is traveling. One material to the one index of refraction to another material of a different index of refraction. This bend increases as the angle of entry decreases. Eventually, the angle is small enough to prevent the light from entering the other end. This is the critical angle that total internal reflection takes. It's a phenomenon known as Snell's law. The light angle is basically outside of the cone or the critical angle, then refraction is going to take place. If it's inside the critical angle, then total internal reflection is going to take place. So when you apply this to a fiber, if you look at the green ray, it's inside the cone of acceptance, okay, which is the same as the numerical aperture. And total internal reflection is taking place because it's inside that critical angle. The red ray is outside the critical angle, and as it couples into the core, it basically refracts or escapes. Basically has a homogeneous core of the same material and only has one mode for the light to propagate down. Multimode, because of its bigger diameter, basically allows for multiple modes or pathways of light to travel down. This is offset and helped by the fact that the core is not homogeneous. It's very subtle, different layers of index refraction, and it makes the light bend in more of a sinusoidal state as opposed to being a sawtooth style state. So what is a wavelength? A wavelength is basically defined in distance in nanometers between one point of a wave to the corresponding point of the next wave. We measure wavelengths in nanometers for optical systems, and that's 1/1000th of a meter. There are some standard wavelengths for both single mode and multi-mode. Single mode has optimized operating windows at 1310 nanometers and 1550. Multi-mode fiber has optimized operating windows at 850 nanometers and 1300. All light that's transmitted in fiber optic systems for the means of transmission are basically up in the infrared spectrum. There are lights in the visible spectrum, like in the 720 to 760 nanometer range, that are used for fault locating or testing continuity. These are called visible light continuity devices, or VHLs, visible highlighters. Power is the same as it is in copper-based systems. It's measured in decibels. It's a ratio of the power in versus the power out of a link. It limits the distance that the signal can travel by causing loss or lowering of the amplitude. Some of this loss or attenuation is inherent in the glass. This is called intrinsic loss. Some of the attenuation can be induced by people in the environment in things such as splices or connectors, or microbends or macrobends. If you look at the natural loss values of silica glass, you'll see that there's, again, those key operating windows of 850 and 1300 for multi-mode and 1310 and 1550 for single mode are based upon low even points in this natural loss spectrum. You'll also see is that there's some hydrogen absorption peaks, like at 1383 nanometers. And then the infrared absorption of silica glass at around 1650 nanometers, basically the loss becomes very, very high at that point. And that's why we have these natural operating windows that we try to optimize on. Absorption. And it's basically the natural impurities, or the hydrogen ions, that absorb the photons that are flowing down the core itself. The other one that's an intrinsic attenuation is called scattering, more specific Rayleigh scattering, and they're natural minute particles of metals that are inherent in the glass when it's being drawn that scatter the photons. Typical intrinsic attenuation for fiber, for single mode fiber, is in the neighborhood of 0.4 dB per kilometer at 1310 and 0.3 dB per kilometer at 1550. Multi-mode systems have a higher loss value at, again, nominally around 3.5 dB per kilometer at 850 and 1.5 dB per kilometer at 1300. These loss values can vary depending upon the specific cable type, and again, the specific parameters associated with the loss values that the manufacturer will guarantee. And the values for things like the connectors and the fusion splicing, they range across all wavelengths. And again, it's for connector losses, they're somewhere in the 0.25 dB loss to 0.75 on a connector that's considered going lossy or being very bad. Fusion splice loss values are somewhere in the neighborhood of 0.05 to 0.3 dB per kilometer. And again, these loss values can vary depending upon the reference standard and the type of splicing. For example, mass fusion versus single fusion, as well as is it indoor cable versus outdoor cables. Extrinsic attenuation that also takes place are, again, caused by man. They are values that are not desirable. The first one is macrobend, and these are large angle bends where as you bend the fiber, you're changing the critical angle between the core and the cladding, and the light is allowed to escape. And the same thing is taking place. Critical angle is changing between the light rays in the core and the light's being allowed to escape from the core. The other value that we're going to talk very briefly about, because you can go into a lot more detail about it, is dispersion. Dispersion limits basically is the maximum bit rate you can transmit to a system, or the maximum amount of bandwidth that you get from point to point in a system. This is basically what happens is the pulse starts to broaden, and they broaden past the duty cycle, and they start causing error codes. The dispersion total is made up of either modal dispersion or chromatic dispersion, and then there's a third dispersion called polarized mode dispersion that I'm not going to cover that deals with very high bit rate systems. Modal dispersions dominate multimode because, again, the multiple pathways of light that are going down the core, and that they arrive at different times. Single mode fiber does not have modal dispersion, but it does have chromatic dispersion. And there's no modal component, and it's made up of material dispersion and waveguide dispersion are the elements that make up chromatic dispersion. And this is why there is more bandwidth capability in single mode than there is in multimode. Diameter, and it's actually in single mode fiber, is that the energy of the photons is actually traveling not just in the core, but in an area just outside the core in the cladding. This is what's called the mode field. The mode field is a description of the light carrying region of single mode fiber. Again, it includes the core and a small region of the cladding. Bending-induced loss of fiber and splice loss is affected. The mode field diameter is a function of the core diameter, the wavelength, and the refractive index difference. And it's about 10 to 15% larger than the core. And one thing you'll notice is that the mode field actually gets larger at 1550. And this is why the difference between 1310 and 1550, at 1550, the fiber is more bend sensitive because more energy has already passed the core cladding barrier, and therefore, if the critical angle changes, will escape very, very quickly. With capability, and what you're seeing here is a curve that's showing you is that the optimized point for the lowest chromatic dispersion or the greatest capability of carrying bandwidth is actually optimized at the 1310 window. The zero dispersion point for chromatic dispersion in single mode fiber is typically around 1305 nanometers. And what this means is that there is more bandwidth capability at 1310 than there is at 1550. However, at 1550, the natural intrinsic loss of the fiber is lower than it is at 1310. So you can go further from an amplitude of the pulse, but you cannot, the pulse broadening is more sensitive at 1550. Another element is what's called cutoff wavelength. We said single mode only has one mode of propagation. Well, that's 90% right. If you go below a certain wavelength, a second order mode starts to propagate. And the cutoff wavelength in single mode fiber is typically around 1250 nanometers. So that means below that, you start getting multiple modes of propagation, therefore more bandwidth issues. But above that cutoff wavelength, which is where we're typically operating at 1310 and 1550, you're basically operating in a single mode of operation. Binary code, you're seeing an example of binary code where you have pulses of light. There is a threshold for the receiver that's looking for that any energy above that threshold is considered a 1. There's also a duty cycle or a period of time based upon the bit rate or the available bandwidth. So for example, a 1.544 megabit system is operating with a duty cycle or the period of time between one pulse to the other of 125 microseconds. The higher the bit rate, the shorter the amount of time between the duty cycles of the pulses. So therefore, if you have dispersion, you'll have the pulse start to spread. And if you look at the second grouping there, you'll see that excessive dispersion has taken the binary code from 101, while the detector on the far end is basically seeing as 111. If you have excessive attenuation, the pulse amplitudes drop below the receiver threshold, and the detector on the far end basically is seeing nothing but zeros because there's no energy above it. You have different design objectives. You have an outside plant cable set of design objectives and an inside plant. The outside plant design objectives is you want to take those fibers and you put them into a cable type that isolate the fibers from external forces. These are external forces that it would see during installation as well as potentially during temperature cycles and time. So things like tension, crush, twist, flex, and compression all can again impact the transmission characteristics by increasing attenuation and loss. We also want to prevent moisture ingress that causes corrosion to the armoring or any metallic elements that are in the cable, or coating degradation to the optical fibers that again protect the fibers as far as a hermetic seal. And you certainly don't want moisture freezing inside the cable because when it freezes, it expands and potential can cause macrobends. You also want to prevent UV degradation of the outer sheath because the outer sheath basically is what protects the core of the fiber. So again, you want to basically make sure that you're addressing the aging of the cable from a UV degradation standpoint. That's why we put carbon black into cable sheaths of our outside plant because of if they're exposed to sunlight, such as an aerial application, they'll degrade and age. Outside plant cables, we're also looking for a temperature range, basically for operation and storage at minus 40 degrees Celsius to as high as plus 70 degrees Celsius, and then for installation, minus 30 to plus 70. Inside plant cables have a different sets of criteria. You do want to physically protect the cable, but you're also concerned about compliance to the National Electric Code for fire resistance, smoke generation, and toxicity. The National Electric Code recognizes 3 different cable types, one general purpose, then riser, and then plenum. Each one of these have different levels of required performance for fire resistance, smoke generation, and toxicity. We also want to isolate, as I mentioned, the fibers from external forces that might be seen during the installation process, which are not as rigorous typically as they are in outside plant. But again, it's tension, crush, twist, flex, and compression. Temperature range typical for inside plant cables is installation operation at 0 degrees Celsius to plus 70 C and storage at minus 40 to plus 70 C. Called loose tube or loose buffer, where you have buffer tubes that may be either dry with water blocking elements in there or gel filled in order to block mitigation of fiber down the buffer tube. They're either armored or dielectric. Armored are typically used in aerial applications where you're concerned about rodent attacks or direct buried. And dielectric are typically used in conduit-based underground systems or aerial if you're not concerned about rodent attacks. You have a ribbon-style fiber, which is a matrix of 12 fibers that are epoxied together in a encoded epoxy. You also have what are called unitube designs, which is basically a single buffer in the center of the cable. There are self-support type cables. One is a figure 8 cable that the messenger is integrated to the core of the cable, and the other self-support is a technology called ADSS, or all dielectric self-supporting. There's a new generation of ribbon cables called foldable or collapsible ribbon. Our trademark name is called wrapping tube cable. And they are also cables that are called indoor-outdoor cables. They have the attributes of the requirements of an outdoor cable, but they have the fire resistance requirements for riser entry into the going into the building. And then there's also another new generation of small diameter cables called microcore cables or micro cables. A listing for the National Electric Code of either general purpose, riser, or plenum. The first one is called circular premise cable, or CPC. There's CPC ribbon, which is basically a circular premise cable that has a traditional ribbon in it. There's indoor foldable ribbons or collapsible ribbons, again, what we call our indoor wrapping tube product. There are indoor-outdoor loose tube cables, which again qualify for both the code listings for indoor requirements as well as the rigors of resistance to the outside plant environment. There are indoor-outdoor foldable ribbon wrapping tube cables. There are also cables that are called air-blown or air-assisted installation cables. We call one EABF, which is basically is a listed indoor cable that utilizes a air jetting system. And then there are your typical, what we call cordage, which are simplex or zip cords, which are pre-terminated with connectors, and these go from your fiber management shelves to your active transmitter and receiver elements. Critical element, of course, is the cable tensile requirements or maximum tension. There are two public straits. One is for short term or during the installation. We call this the dynamic installation tension, or the cable is under tension. And then there's long term or in operation. This is when the cable is in a residual or relaxed state. For your outside plant cables, your typical installation tension is a maximum of 600 pound pulling tension. And your static or operating tension basically is at 200 pounds. Inside plant cables are typically 200 pounds installation and 120 pounds operation. You also have an element called the cable placement, or the maximum bend radius or bend diameter. Each cable has, again, two bend radiuses. One is loaded during installation or dynamic, and the other is unloaded or long-term, which is called the static or the relaxed state. Again, both inside plant, outside plant cables typically have a 20 times the cable diameter as allowable bend radius for the dynamic or installation, and then 10 times the cable diameter for the long-term, such as coiling or static bend radius of the cable long-term. So to terminate, there's a fusion splicing process so that we actually fuse the fibers together. This is done either for mass fusion for ribbon cables, either traditional matrix or the foldable collapsible type. They use fiber holders to hold the fibers in place. You also have single fiber fusion systems that also have fiber holders that hold the fibers in place and basically speed the process up of the stripping, then cleaving, and then the fusion splicing process itself. These are typically automated systems. They've become very quick in their processes. Thermal strippers for mass fusion now cycle at 8 seconds as opposed to at times they used to be up at the 30 seconds to a minute. They're now much quicker. Thermal strippers are also basically an independent. They're not sucking power off of the battery for the fusion splicer itself. They have their own battery systems. In single fusion, we use a mechanical stripper. When the fibers have been stripped, they have to be cleaned with a fiber cleaning solution, which is a 90% regrant alcohol or a special fiber preparation fluid that leaves no residue on the fibers. Then they're cleaved to ensure a perpendicular 90-degree end face as much as possible. And then they're put into the splicer that basically does the fusion splicing process. A ribbon splicing process is a cladding alignment, and typically the single fusion splicing processes are using a core alignment. Stripper that's used in mass fusion shows you the fiber holder that's used in splicing traditional matrix ribbon or spiderweb ribbon, or foldable ribbon. And then you see the cleavers. The newer cleavers and the thermal strippers actually communicate to the splicers via Bluetooth and give feedback to the technician to understand, the splices being affected possibly by the cleave quality and the number of cleaves that you put on a particular blade section. So when you splice in the field and you're in that outside plant environment, you have to put the fiber in a protective enclosure. These are called splice closures. This is an example of an AFL closure. The closures now are new generation of closures that use a gel entry system. They'll have baskets for mid-cable access, and they'll have splice trays that will accommodate either single fusion or mass fusion. They also have a sealing method to assure that there's no leaks, so that you can actually flash test them to determine that you've got a good seal on the cable entry points as well as the O-ring that seals the base assembly to the dome. Again, closures typically will have either a gel entry system or they'll have a grommeting system or grommeting technology on the new generation closures out there today, where the old styles were using heat shrinks and rubber mastic tapes and washers, washer-based systems. The newer closures that are using gel entry, again, very fast, very few piece parts to assemble, and typically the ports are independent of each other. Therefore, if you're going to add a cable to a closure, you don't impact the existing cables that are there. But all this is to assure that you protect the splices, whether they're stored in an aerial environment or in an underground handhole, and that the doesn't become an ingress point for moisture that may impact the fiber technology. So this is the end of the presentation. I appreciate your attention and open the floor if there are any questions.